We're going to talk today about conservation of energy. As I turn the lights off to conserve energy. Not the same word, right? Conservation of energy in physics, though, means the idea that energy can neither be created nor destroyed. Okay? Mechanical energy. So what you put in, you have to get out somehow. Okay? You're not going to lose that energy just to nothing. Now, we'll talk about how mechanical energy can eventually be transferred into like energy loss and friction. And the energy is still there, it's just that friction has taken energy away from that. So we're going to look at situations where it's conserved, and we're going to talk about different types or forms of energy, which you've seen. Let's go through how they actually work. So this looks like a whole lot of mess, right? And it looks like a lot of symbols and stuff, but it's actually pretty straightforward. Let me go through this one step at a time. First, the conservation of mechanical energy theorem tells you the sum of the potential and kinetic energy in a system at any point in time is conserved from beginning to end, or it's constant. It's the same when friction is neglected. Now, that's what this says right here. This right here, take a look, is what you have on your formula sheet. This is what you have on your formula sheet. So, you can't just say, oh, MEI, MEF. You have to know what those are. ME just means the mechanical energy. What does I stand for? And F? Final. So beginning and end, right? At stage 1 and at stage 2. So let's look at an example of this. An object, before we go into the further stuff. An object is here on the top of a cliff. It's not moving. What kind of energy does it have? Why?
Because it's not moving and it is going to move.
Okay, close. I like the idea. Give me more. It has a height with respect to the ground, so it has potential energy. So this object right now is not moving, but because it has some height above the ground, it's got potential energy with respect to the ground. It could fall, like Zero was saying, it has the potential to move. Now, so in the beginning, we could say that it has potential energy. Let's write that down at the top. At the beginning, it has potential energy. How about halfway down? As it's falling right here, right? So it gets kicked off. And now the object is here, and it's falling. So what kind of energy does it have now, Benno?
Kinetic energy?
Kinetic?
Yeah.
Agreed. What else?
Potential energy?
Still has potential, because it's still above the ground. So at that stage, it has both. At that stage, it has both. Now, the instant before it hits the ground, it's still moving, okay? But let's say it's pretty much at the ground, but it's still moving. Okay, it's at the ground. I'm going to tell you, you could assume it has no height, even though it has like an infinitesimally small height above ground. Theo?
Does it still have a potential energy or no?
No potential, so what does it have?
Kinetic energy?
Yeah, okay, so it's the instant before it hits the ground. Once it hits the ground, it loses energy to its actual compression, believe it or not. It's elastic. It's a real spring energy. If you dribble a basketball, why doesn't it come back up to where your height is if you just drop it? Why does it only go up to like halfway?
Friction.
Friction.
It loses some energy.
When it...
It bounces against the ground.
Yeah, but what happens to the object itself?
Well, when it's going down, it's being pushed down by gravity, but when it's going up, it's being pushed down by gravity, right?
But due to conservation of energy, it should come up to the same height. If it has 5 joules of energy here, right? And all that energy is converted to kinetic and hits the ground, as it comes back up, it should go back up to the same height with 5 joules of energy still, but it doesn't. So the question is, why doesn't that really happen?
Does the ground absorb some energy?
The ground, so friction was one of the comments, which would be friction between the ground and the object, is one way of losing energy.
Is the amount of air that's in the object, or is it like
Not air, it has to do with that, but it's not the air in the object. Think about an object that you're dribbling or bouncing. A tennis ball, a basketball, a soccer ball. On impact, the ball compresses. You can't really see it. If you look at a high-speed camera of a baseball being hit, it's actually pretty amazing. Baseball definitely compresses when it hits the bat. A basketball, when you dribble it, when it hits the ground, it literally compresses. It's pretty amazing. It happens so fast you don't notice it. Okay? Because the air inside, it's a malleable, it's a membrane, right? The basketball itself is a membrane. It's flexible. I mean, it's difficult to squeeze yourself, but it can be flexed. Ever use like a tennis ball? Like take a tennis ball in your hand, you can squeeze a tennis ball very easily, right? It's not difficult to compress a tennis ball at all. Okay? When I bounce this ball, it bounces back up. When I do this, it compresses. It takes me energy to do this. And then when I let go, the energy that's being stored, this is like a spring. Think about a spring. A spring you compress and then it expands, right? This is a spring. That's why I said springs are so important. They're modeled by everything. Everything's modeled by springs. So I compress the spring, and then I let go, it goes back to the size. Because when I'm compressing, I'm storing energy. When I let go, it expands back to its original state because that energy pushes back out. So when I drop this, due to conservation of mechanical energy, it should come back up to the same height. But it comes up to like what, 50% of the height? And then on the second bounce, it comes up to like half of that maybe, and then half of that. So it loses about 40% of its energy respectively every time. I drop it from here, it comes back up to about 60% of its height, which means it loses about 40% of its energy. On the next bounce, it loses another 40%. It's exponential decay. Think about, have you done anything with exponential functions yet in math? Did you do exponential decay in chemistry? Half-life? Does that ring a bell? This is a half-life. Think about it, 1 second. But it's not a half, unless it was exactly half at the time. Half the height of the first bounce, about half the height of the second bounce, about half the height of the third bounce. See how it's halving every time? Its height above ground, or its energy, is decreasing at an exponential decay rate because it's losing energy to the compression, and it's also losing energy because of the friction in the actual bounce. So conservation of mechanical energy is conserved, but in real life, there are things, and that's what we're going to see this Q loss at the end over here. There are things that are going to throw that off though. This Q loss at the end accounts for all energy lost. I put a lump sum there. It could be friction, it could be air resistance, it could be the compression of the object, it could be anything. But Q loss, that's the energy lost in the system. Okay, that's what makes it not really balanced. We'll talk about how that works. But the idea is that at the top, it's all potential. Here, it's moving right here. I'm pausing, freeze frame. It's still moving, and it's got height. So it's kinetic and potential in blue there. And then the instant before it hits the ground, it's moving, but it technically has no height, so it's all kinetic energy here. And we can set the kinetic energy at the end equal to the potential at the top. Because we were told due to conservation that at any point in time, the overall energy is constant. So I could say this. I could say that the potential at the top equals the kinetic at the bottom. Or, if I wanted to solve for something, maybe I'm looking for a certain variable, and we're going to do this today. Or I could say that the potential at the top equals the sum of the kinetic and potential midway. Or the kinetic and the potential midway, the kinetic and the potential at the midway point could be equal to the kinetic at the bottom. But at any instant in time, the energy is equal. So as long as you can identify what kind of energy it has, you could always set it equal. So the kinetic at the top equals the sum of them in the middle, which is also equal to the kinetic, or the, potential at the top, equals the sum of them in the middle, which is also equal to the kinetic at the bottom. Any of those are true. This is for this one instance right here. This is not like a general rule that you're going to be using. I'm just writing down the scenarios. So if you can identify the type of energy at an instant in time, you can set that equal to the energy at another instant in time, as long as you know what kind of energy it has. Okay, so energy at any instant equals the energy at any other instant. That is what the mechanical energy conservation tells you. This right here literally says that. The total energy at any point in time is equal to the same as another point in time, which equals the energy at another point in time. But the type of energy changes. That's why on the second line here, ready? I put this symbol. What does this mean again? Who remembers from Newton's laws?
The sum.
The sum. So this means the sum of the potential and kinetic energies at some point in time equals the sum of the potential and kinetic at another point in time. Well, here there was only potential, right? Take a look, please. Here, there's only potential. So technically I could have done this, right? For that instant. But then in the midway point, I've got both kinetic and potential. So they're both there. Well, that is this equation right here, right? There's really a kinetic in the beginning also, but it's got no kinetic energy in the beginning, so it drops off. So you could always start by writing this formula right here, and then drop off whatever kind of energy it doesn't have at that instant. So when it's at its max height and it's not moving, it's only got potential. So this gets dropped off. Maybe we're trying to figure out the velocity at the end, so it's got no potential at the end, so we could drop this off too. And then this would lead us to that third equation down here at the bottom at this point. Potential at the top equals kinetic at the bottom. Whoops, this is the first equation. I'm crazy. Okay, the first equation, not the third equation. So the idea, though, is that the total energy of the object at any instant has to be conserved. You have a question at one point, right? Push it away for a second.
So the loss comes from the energy it takes to compress the ball, right?
There's many things, but we're going to lump it together as a parameter called Q loss. I'm going to say energy loss. Q means energy. You remember Q equals MC delta T? Instead of just using capital E for energy, I'm using Q because usually it's lost to friction and there's some heat loss involved, right? Some heat, because of friction you involve heat. So I use Q loss. I don't know, I kind of invented that one myself, to be honest.
And is that a constant that you're gonna give us, or?
That might be like the amount of energy you need to figure out is lost in the system. If I tell you the potential in the beginning is 12 joules, but at the very end it's only got 9 joules of kinetic, how much do we lose? 3 joules, that would be Q loss. The difference between energy levels at any given point in time. Maybe I'll tell you that from the top to the end, it loses 5 joules of energy. That's Q loss. So maybe you have 15 joules of potential at the beginning, okay? And I tell you it loses 3 joules. And at 15 at the beginning of potential, you lose 3 joules of energy along the way down, leaving you behind with 12 joules at the end. You could set that 12 joules equal to 1/2 mv squared and figure out the velocity at the very end of the problem. That's kind of what we're going to do today. We're going to substitute those formulas you've been using in section 5.1 and 5.2. The work formula, FD cosine theta, the kinetic energy, 1/2 mv squared, the potential energy, which is mgy, the spring energy, which was 1/2 kx squared. Any of those will come up, and we're going to do examples of that now. Okay? So again, with friction involved, this overall equation, which is really the sum of potential and kinetic, becomes really this. You lose energy. So think about it. If the energy in the beginning is like 15 joules, that goes here, for this side, right here, right? 15 joules. And then the energy at the end, let's say there's only 11 joules of energy. Well, what must Q loss be then? Anybody?
4?
What must Q loss be, Frank?
4?
Yeah. Okay, that's all you have to think about. Okay, so this 11 joules is like how much energy there is at the very end in potential and kinetic. That's this 11 joules right here. Okay, this is what this comes from. Well, what's left over? How much energy is lost? So 4 joules were lost to friction, to air resistance, to the compression of the object, to whatever it may be in that instance. Okay, it's a generic term. God bless you, Emma. It's a generic term simply because all of these things come into factor. The actual energy loss to friction, the heat loss, the compression of the object, if there's an impact, all of those things involve loss of energy. So we're going to lump that together in one parameter. Okay, a good term to write down. You can write this down if you want, a lumped parameter. Q loss is a lumped parameter. It's a term you'll use if you end up studying physics or engineering in college, a lumped parameter. Similar to K. Remember the K value for a spring? K is the spring stiffness or the spring constant. K is a function of the spring's length, the spring's coils, the material itself, the diameter of the spring. We lump that all together in something called K. We're not going to take into account all those minor parameters. It's a lumped parameter. Okay, conceptually, thinking about a pendulum swinging back and forth. I can demo, but it's pretty straightforward what a pendulum actually looks like. So a pendulum swinging back and forth. Okay. It's pretty much like, when you see like somebody trying to hypnotize someone. Like you're getting very sleepy and they just kind of wave a stopwatch back and forth in front of their head. That's exactly what a pendulum is, obviously. Okay, so here's an example of this. So here's a pendulum. Okay? Please don't get very sleepy. It's a pendulum. When it's up here and I'm holding it still, I let go. What happens to it? What happens, everybody, when I let go? It swings. Because what kind of energy does it have right now? Potential energy. When it's at the very bottom of its height, call this ground level, right? Remember, ground level is a relative term. I'm going to call this ground level now. What kind of energy does it have? Imagine it's moving, right? And it gets to the bottom. What kind of energy? All kinetic, because it's got no height. What about here? It's got height and it's moving. Both potential and kinetic. And when it gets to the top and it stops, what kind of energy? Just potential. Then it comes back. Kinetic and potential until it gets to the bottom. All kinetic, because it's at the bottom. So this is a constant transfer of energy. I'm moving my hand, which is keeping it moving. But if I let it go, what will happen eventually? Because of loss to friction or the resistance in my hand. But Q loss, the energy that it's losing, is what causes this to stop. If there was no Q loss or no energy loss, no matter what, this would technically go on forever. Okay? And it doesn't. It does not go on forever. It stops relatively.
Something to do with gravity, like in space, would it go on forever or not at all? Or go on
In
for
space,
longer?
if you had something like this, it would never fall because there's no gravity. Right? I had to think about that, but that's the answer, right? In space, there really isn't potential energy because it's got no, what height relative to the ground doesn't matter because remember potential energy is mgy. G in space is 0. So you start up here in space and you go to let go, you let go. It doesn't move because it has no potential energy. Energy is very different when you're not in a gravitational field. Okay, remember the energy we're talking about.
What if you have less gravity? If you're on like another planet?
If you have less gravity, it just means you have less energy at this height, so it would move very slowly and you wouldn't have as much velocity at the bottom. Because less potential at the top, right? Let's think, that's a great question. Less potential at the top because of the moon. You're on the moon, you have 1/6 gravity, so the potential at the top would be 1/6. And if all that potential is converted to kinetic, it means the kinetic at the bottom is 1/6 of what it would have been. If the kinetic is less, kinetic is a function of velocity, so the velocity would therefore be less. So if you drop something on the moon like this, it'll go like this, ready? Instead of going like this. See how much faster it goes when you let it go on Earth? This is the moon. Because the potential at the top is very little. So it's got less energy, so less energy is converted to kinetic, so less kinetic energy at the bottom, therefore less velocity at the bottom. Remember, kinetic energy is 1/2 mv squared. M is mass, that's not changing no matter where you are. Velocity has to go down if the kinetic at the bottom is less.
This might sound like a stupid question, but
Probably not.
So, like when you keep on saying, right, like when you go up to something and then you drop it, the potential is converted into kinetic energy, right? It's basically all a theoretical thing. I mean, like,
Of course.
it doesn't actually like have a potential energy that's. I mean,
We've come up with this term potential energy to measure an object's energy as a function of its height or state in time or space.
So when you drop something, you just.
It's all because of gravitational fields. So gravitational fields are what cause energy change. It causes you to move when you drop an object. If there's no gravitational field, you let go, it's not going to move, so there's no potential, because there really isn't any gravitational field. It's not dropping, so there's no kinetic. So this whole idea of conservation of energy, yeah, that occurs within a gravitational field. Okay? And yeah, it is theoretical. It's highly theoretical, but it works. And the math behind it is amazing that it works out. You can solve a lot of projectile motion problems using energy methods, and it's a lot easier. So when you're doing the midterm, you're going to see one problem in the midterm, I guarantee I'll put in parentheses, either use projectile motion or energy. I would recommend energy methods. You're going to see after today that it's a lot easier to use energy methods than projectile motion whenever possible. So the conceptual idea was the bob swinging back and forth. We already talked about that. The numerical example is what we talked about with the tennis ball. Okay, what happens in the beginning? It's at a height of 1 meter. It hasn't been dropped, so times 0. It's at a height of 1 meter. It's not moving, so how much kinetic energy does it have, guys? If it's not moving, how much kinetic energy? How much? Anybody? None. It's not moving, right? So kinetic is 0, and it's got potential. So if I add these two together, what do I get? What do I get when I add these two numbers together? This is not a trick question. Yeah, so the total energy is 0.74. That's what this column is. Take a look. Notice, isn't the total energy the same every time? Because mechanical energy is conserved. The total energy of the system never decreases. What happens though is this. Look, the potential energy goes down, doesn't it? But what happens to the kinetic energy? It goes up. So there's a balance. It's like a seesaw, literally. It's a balance of energy. At the top, it's all kinetic. At the bottom, it's all potential. In the middle, it's a little bit of both. So as this object falls further, it decreases in potential energy. Do you see that? Everybody see the potential energy decreasing? But what's happening to the kinetic energy? And at the end, though, if you sum this and this, you still get this. Add this and this, you still get this. Add this and this, you still get this. I don't know why they didn't just round this to 0.04. It would add up exactly. It doesn't make sense not to make that point. This is from your textbook. Okay, that should really be 0.04, not 0.036. Just to prove the point that it's still 0.74. What about when it hits the ground? Right, so this continues to happen. The height continues till it gets to 0 meters of height. What's the potential energy when it's at the ground? When it's on the ground, how much potential energy does it have? 0. So therefore, what would the kinetic energy be at the ground if we're considering the fact that this has to be conserved the whole time? 0.74. Okay, when it gets to the ground, all the energy is kinetic. All the energy is kinetic the instant before it's the ground. None of the energy is potential. Okay, 0 potential, all kinetic. Therefore, when I sum them together, I still get 0.74. So the idea of conservation of mechanical energy is that at any instant in time, the total mechanical energy remains the same. The sum of potential and kinetic. Now, if you have a spring involved, it just gets lumped into that also, potential energy. We'll talk about how springs work also. For your lab to finish, all you need is this knowledge. Think about your lab. Let's stop for a second and go to the lab. The instant before you toss the tennis ball, right, we'll consider that to be like ground level. This is your horizontal axis. We'll consider that to be ground level. That's why you made your origin, where you release the tennis ball or the object you kicked or threw. So it's got 0 potential at the bottom. When you let it go, it's got velocity. So what kind of energy does it have? If it has velocity, what kind of energy does it have? Velocity indicates which type of energy, potential or kinetic? Kinetic. So in the beginning of your lab, it's all kinetic. When it reaches the top of the path, it's got height, and it's still moving horizontally. So it's got potential up here, and it has kinetic at the top, because it's still moving. Even though it's stopped vertically, it's still moving horizontally. Then it gets back to here, and at this point in time, it's going to have all kinetic again, because it's at ground level. So here's the example I'm talking about. Ready? I toss this object from the table's height, which is 0. This is the ground. It's got no potential. It's got velocity. And at the instant I throw it up here, at the top, it's still moving, and it's got height. So here, it's all kinetic energy, because I gave it some initial velocity, but it's got no height. So this is all kinetic energy. Up here, it's got potential energy, because it's got a height, and it's still moving. Right? It's still moving horizontally, even though it's stopped vertically, so it's come back down. So it's got potential and kinetic at the top. And at the end, it hits the ground again, it's got all kinetic, no potential. So in your lab, you're going to see that you're going to have to utilize these different forms of energy to calculate. Okay, and you'll be able to go through that. And I kind of step you through every single step along the way. Let's do an example, though, to make sense of this. Your lab, let's do the example. It'll make a lot of sense. Starting from rest, a child slides down a frictionless ramp. Why is it important that it's frictionless?
So there's no loss there.
Yeah, there's no Q loss in this problem when it says frictionless. You can tell already. On a skateboard, if the height of the ramp is 4 meters, then determine the speed of the child at the bottom of the ramp. So this seems like it might be difficult. It's like, oh, well, this is an inclined plane problem. This is going to be very difficult to figure out. Well, it's not, because at the top, here's the person on the skateboard, right? I'm just going to put a circle. And here's the person at the end on the skateboard right down here. Some point in space. At the top, it says starting from rest. So what's the kinetic energy up at the top if it's at rest?
0.
Very good, Sarah. Okay, it's at rest. The kinetic energy initially is 0. But it has some what? We don't know what it is yet, but it has potential. Very good, at the top. And I'm going to call this the initial location. You could use 1 and 2. You could say at stage 1 and at stage 2. You could say KE1 is 0, and PE1 is some number. And then at the end, call this KE2 and PE2. It does not matter if you call it 1 in the middle here, call that stage 2. At the bottom, call that stage 3 instead of I and F. That's fine with me. Does that make sense what I'm saying? You don't have to use I and F for like before and after. At the end, when it's at the bottom, what's the potential energy at the bottom?
0.
Why? It has no what? Height. Potential energy is a function of height or compression for springs. In this case, it has no height at the end, so the potential energy at the bottom is 0. What does it have since it's moving? It has kinetic at the end. So we start with our conservation of energy formula. We say the following. We list our energies. Clearly, it's got no kinetic in the beginning, so I can cross that off. And at the end, it's got no potential because it has no height, so I can drop that off. So look already how much simpler this formula is, because I've identified the types of energies at different states in time. So PE initial is all the energy, KE at the end is all the energy, so those two things are equal to one another. The energy in the beginning equals the energy at the end. So we go ahead and continue this down. Again, we've got PE initial equals kinetic at the end. The formula for potential energy? The formula for potential energy is what? Anybody remember? Potential energy, and?
1/2 mv squared.
That's kinetic. I'll put it over here.
Oh, mgy.
What is it?
Mgy.
mgy. Now, I'm putting an I for y initial, meaning the initial height, and I'm putting an F for the final velocity. Those are subscripts. Is that clear? Yi means initial height, Vf means final velocity. We know the height of the ramp. We were told the height of the ramp is 4 meters. If we were told the length of the ramp, could we figure out the height? Sure, using
Pythagorean theorem.
or, if you didn't know the width, you couldn't do it. Trigonometry, if you knew the angle. Okay, if you knew the angle, say you knew the angle was 20 degrees, and the length of the ramp was 8 meters, you could find the y component by doing 8 meters times the sine of 20 degrees, that would give you the height. But in this problem, I was nice, I gave you the height of 4 meters. Okay, I gave you the height of 4 meters. This is a child on a skateboard. So what could you tell me about the mass before and the mass afterward? It's the same. Unless along the way, like somebody threw an object and the person caught it, right? So I'm sliding down this ramp and Theo throws a football at me and I try and catch it. Well, my mass initially is going to be less than my mass at the end because now I'm in football also. So I would need to know the mass in that kind of a problem. But because the mass in the beginning is the same as the mass at the end, what happens to those masses?
Oh, they cancel out.
It's the same exact number. If this is a 5 over here, it's a 5 over here. They cancel because everything is factors now, right? They're all multipliers. When you have multipliers on both sides, they cancel out. I saw a hand in the back. I saw a hand shoot up.
I was just saying crossing
Nice. Okay. So our question here is to figure out the velocity of the object after the person has gone down the ramp. So figure out what Vf is pretty much. Okay, and this is easy to solve generically. Multiply by 2 to get rid of the 1/2. And take the square root. And I'm going to put a plus or minus here. Tell me what you get as a number, please. 2 times 9.81 times the height of 4 meters under the square root.
8.86.
8.86. That's what I got also. My units are what? What are my units? It's measuring speed or velocity. The units are what? Good. Now, this problem literally said, determine the speed at the bottom. Speed has no positive or negative sign, so I don't need this anymore because it said find the speed at the bottom. Even though the formula is solving for velocity, the speed is just a positive value always. Now, I'm going to do something in a moment that's going to blow your mind. Are you ready for it? Seriously, it's going to blow your mind. It's pretty cool. Write a little side note over here somewhere.
And this one's gonna blow our mind.
It's going to blow your mind. Get ready. Start with this formula.
Oh, it's going to equal.
Take a look at this formula. And take a look at this formula. Which of these 3 formulas do you think would enable us to find the actual velocity at the end? Remember, we're trying to find Vf, the velocity at the end. Which of these 3 formulas can we roll out right away? Which one will we not use?
First one.
Yeah, the first one we're not going to use because it doesn't have VF. Are we given anything about time in this problem? Is time involved? So which formula are we going to use? The middle one. What's the initial velocity in this problem, guys? Because the object or the skateboarder starts from rest. So cross this off. Solve for VF. Take a look. Take the square root. It's the square root of 2ay, isn't it? Look. The same exact formula, completely different ways of doing this. One energy, one projectile motion. If you solve for VF here in the red circle formula, it would be VF equals the square root of 2 times A. A is G, it's gravity, acceleration of gravity, times Y. It's the exact same formula. Completely different approaches, one using Newtonian projectiles, one using energy methods, with the exact same answer. So when you're taking this midterm, you could use either method. There are certain times that I would highly recommend using this method. Okay, if you're not given anything about time in the problem, use energy methods. If you're not getting things about time. If you're given a problem where the mass is changing, use energy methods. Does this take into account? Does the projectile motion formula take into account mass anywhere? So you can't use that. So if you're given anything with mass, use these formulas. If you're given anything with time, use these formulas. If you're not given stuff with time, go to these formulas. But the crazy part is that this literally is the same thing as that. Solve for VF. You get rid of the square by putting a square root around this. This under the square root is the same as this under the square root. It's the exact same answer. Completely different approaches, but with the same exact answer. That's why when people talk about like the beauty of physics and stuff, that's what this is talking about right here. It's amazing to think about the fact that you solve something completely differently, yet get the same generic solution in two completely different ways. Okay, and you'll see that occur a lot for the rest of the year. You're going to notice formulas that come up again, and you're like, wait, I recognize that solution. Didn't we see that before? And that's where it comes into play. Okay? All right, let's take a look at the blown, but I'm seeing figuratively a lot of those, right?
I
Just
kind
like,
of
whoa.
expected more. I thought you were gonna like discover the root of the Illuminati or something.
I did not do anything like that. It was a simple mind-blowing
It
thing,
was
yes.
pretty close to it.
But it was beauty of physics in like some simplicity also. That's what was cool then. All right, so let's take a look back at our pendulum, right? Here's our pendulum. The pendulum bob is released from some initial height. We don't know the height. Some initial height. Such that the speed of the bob at the bottom, right? The speed of the bottom is 3 meters per second. What is the height? What is the height of the bob? And at what height will the potential and kinetic be the same? So let's take a look at a diagram of this. So we're going to call this ground level, right? Always call that ground level at the bottom of the path of the pendulum. So at the bottom, what kind of energy does it have? Only kinetic. It's moving, but it's at ground level. At the top, what kind of energy does it have? But it's not moving, so it's got no kinetic at the beginning. So, do you recognize more beautiful physics at work? What do you recognize? Anyone? What do you recognize about this problem? At the beginning, before it's released, it's all potential. At the end of the bob, at the end of the path of the bob, or at the bottom of the path of the bob, whatever, the bob is the mass. It's got kinetic. My friend's name was Bob, and he sat next to me in high school physics. He really did. My best friend to this day, Bob Peterson. Bobby, I call him, but it was always like Bob, Bob, Bob. What do you recognize? What's the beauty in this problem? Anyone pick up on it yet?
Oh, there's no.
You know what? You didn't finish the statement. How do I know? Sorry, where you go?
Sounds wrong.
You can't know if you're right or wrong. I'm gonna take a guess. Yeah.
3.
3? No, not 3.
It's all the same answer.
It's all I'm saying. Kinetic energy and potential are the same again.
Okay, so what is this the same as then?
Before.
It's the exact same as the last problem. It's identical. You don't realize it, but it is. In physics, we model things, right? This is identical to the last problem. What kind of energy did the skater have at the top?
Potential.
And when the skater went down the ramp and ended up in the ground, what kind of energy did he have? It's the exact same problem. It's no different. So this is the same exact solution, except in this problem now we're not looking for velocity. We have velocity. What are we looking for? What is the initial?
Height.
So we're looking for y in this problem. I don't even have to write the others. I can write them and then cross them off again. Right? I could write kinetic energy initial and cross it off because there is none. I could write over here at the other end, over here, I could put potential energy final and then cross it off, but it doesn't really matter, right? Because it's 0. So I'm going to list the energy at the beginning equals the energy at the end. I'm going to write my formulas out again. I'm going to recognize that what cancels again? Mass cancels again, giving me giving me this formula right here at the bottom. But now I'm not solving for VF anymore. Remember, the mass has not changed. The bob is the bob, not changing. I want to find out the height of the object, so solve for y. So this problem is the same generic formula, but the solution is not the same generic solution because we're not solving for VF anymore. Oops. Having a brain fart there. I apologize. It's going to be 1/2 VF squared all over G. Now, if you want to, you can write that as VF squared over 2G. Right? Putting a 1/2 in the numerator is the same as putting a 2 in the denominator. Recognize that, please. Do we all see that? Multiplying by 1/2 in the numerator is the same as putting a 2 in the denominator. So I could have written this solution, and I want you to see that because if you're given a multiple choice and I ask you for like the generic solution, you could write it like this also. It's the same exact thing. Dividing by 2 is the same as multiplying by 1/2. Answer field?
0.46.
0.46 units of height? Yeah, good. About a 1/2 meter in height. It's a pretty decent sized height to get it moving at 3 meters per second. What's crazy and what's wild is that the mass of the bob has no effect on the problem. You would probably never have thought that before. Imagine you have an object that's like really light, and you have an object that's really heavy on the end of a pendulum. Theoretically, if they're released from the same height, they'll have the same velocity at the bottom. The mass does not affect it. The velocity of the bottom is independent of mass. Yet, realistically, the object's shape, how much air resistance it encounters, affects a lot of it, right? Okay, if the pendulum itself is not taut, what does taut mean? Not taught as in I teach you, but taut. I say the rope is taut. Yeah, you pull on the rope so that it's tension in the rope. So if the object hanging from the end of the pendulum, right? So look up, this is heavy. It's literally it's a very solid copper or whatever. I don't know, it's not copper. Whatever it is, some alloy metal. It's heavy. So when I let go, there's tension in this rope. You see the tension in the rope? If I put an object with a paper clip on the end, is there going to be a lot of tension in the rope? So we have to assume that there's enough mass to create a tension-filled rope. You would even call this a rod. Even though it's not a rod, you might model this as a rod that is incompressible. This is clearly a rope. It's compressible, right? So you might have a rod. If this is a rod length, and it's a pendulum at the bottom, and at the bottom you have a mass that's like a paper clip versus a mass that's like a bowling ball, if this were a solid rod, technically speaking, it would move with the exact same motion, which is kind of amazing to think about. It's independent of the mass. That's why you also hear, remember, if you drop an object from a building, they should move at the same exact rate. You ever see that video? I should pull up that video. Do you have time? Yeah, we do. 13? Okay. So there's a video. I'm going to pause here. We'll pause at this example. Let's use the diving platform at an angle of 23 degrees with a velocity of 4 meters per second. So I'm calling it a diving platform and not a diving board, because if it was a diving board, it would be a spring, and we'd have spring energy. And we're going to see spring energy, but I want to look at spring energy in the next example. So with a velocity of 4 meters per second, if the platform is 8 meters above the water level, what is his speed the instant before hitting the water? So what does it help you to do? Draw a diagram. Okay, label that diagram. So here's the diving platform. It's sticking out above the water. This person is, let's make believe it's a fixed diving platform, so it can't be all springy. And then here's the water down here. Okay, this is Tom Cruise jumping off a bridge into the water again. He's crazy. Now, we're told that it's jumped at a 23-degree angle. That's my theta value if I need it. I'm told that the initial velocity that he jumps with is 4 meters per second. We're told that the platform itself is 8 meters above the water level. Okay, and the question is, figure out the velocity here. Find the velocity after this person continues the path and ends up right in the water. So, in the beginning of the problem, this is now different than the last two examples where we had all potential in the beginning and all kinetic at the end because it was a pendulum or the ramp. In the beginning, he's got potential. Why does he have potential in the beginning?
He's already moving at 4 meters per second.
That would be not potential, but
Kinetic.
kinetic. So Anthony, good. He's got kinetic energy then because of the velocity. So there is KEI. He also has a height, or she, of what? 8 meters. So there's also PEI. This is all in the beginning. So in the beginning, this diver dives with a certain velocity from a certain height. As a result, he or she has both potential and kinetic energy. Now, when he or she lands at the water, we're going to call the water what? What should we call the water level? Call that? We've been talking about this. Yeah, 0 or the ground. Very good. So go ahead and do this, please. Put a dashed line on the water. A dashed line is a way to represent your ground level, even if it's not really the ground. And usually, you'll see in your book and in the lab we're going to do next week, you're going to see PE equals 0 there, which means this is the ground level. Potential energy is 0 there. So at the end of this problem, the end of the problem for us is when he hits the water. I don't care what happens once he's in the water, fine, do whatever you want. But our problem is find the velocity as soon as he impacts the water. So the instant before he impacts it, really. So we're trying to find VF. If he hits the water, his height has got to be 0. So at the end of the problem, we've got kinetic energy. Do we have potential energy? Bless you.
God bless you.
And that sneeze was no, exactly, okay? So he does not have potential energy at the end there. So the answer to the end is no because of the fact that he's at ground level. And I'm doing this with my hands to mean, quote, ground level, what we call ground level. All right? So we look at this problem, we see that we have a different kind of an example than last class. Again, though, we don't have mass. We're not going to need mass, it turns out. We'll see how that works. So we start with our formula. Conservation of mechanical energy tells me that energy before equals the energy after. Right before this diver actually leaves the the instant he leaves the platform, he's got what kind of energies in the beginning?
The instant before is potential.
Let's say the instant he leaves it. Potential and?
Kinetic.
Okay, again, because he's leaving the platform with a velocity of 4 meters per second. Had there been a diving board, we would have to use 1/2 kx squared, which we're going to see how that works. And it would be a spring. And it would be spring energy and potential energy. There wouldn't be any velocity. The velocity, where does that come from? It comes from him pushing off. Or him jumping on the diving board and the diving board springboarding him forward. The energy at the end of the problem is only kinetic energy. Again, at the end there's no potential. Why? Why is there no potential at the end of this problem? Because yeah, there's no more height available. He's at ground level, which we call the water surface, ground level. Okay, so you could put plus PEF, right? And then just put an arrow saying it goes to 0. So there's our equation. Very, very similar to last class, except in last class we didn't have KEI. We had no initial kinetic energy because this person at the ramp of the skateboarder just slid down the ramp. And then the pendulum was released from rest. So in the last two examples, we have not had any KEI. This is no more difficult than what we've done. Just plug in. Formula for PE is mgy, and since it's initial, I'll put yi. Kinetic energy initially is 1/2 mvi squared. Kinetic energy at the end is 1/2 mvf squared. What do you recognize? What can I do to simplify things?
You can get rid of mass.
If mass is in every term, it can be eliminated. It's like you're factoring it out on the left-hand side and canceling with the right-hand side. If I had a spring, why can't I cancel mass? If I was using a spring, why would I not be able to cancel mass? Anybody remember the formula for potential energy in a spring? 1/2 kx squared. You don't have to memorize it. I'm going to give it to you, but we're going to do that in the next example. A spring does not actually account for the mass. So if I had 1/2 kx squared at the end over here, say you landed on a spring and the spring got compressed or something like that, right? Hypothetically. Or you landed on a trampoline. You want to know how far the trampoline is going to compress? You'd be finding x. So he lands on a trampoline now. Well, there's no mass anymore, so you cannot cancel all the masses anymore. It's got to be at every turn. But because we don't have a spring, obviously, in this problem, we can indeed cancel mass, making our equation a whole lot simpler. I should multiply by 2 everywhere to get rid of my 1/2s, make life easier on me. When I multiply the left-hand side by 2, I need to remember to distribute the 2, which yields 2GYI. And then the 2 times the 1/2, those cancel for VI squared. And then the 2 times the 1/2 over here leaves me with VF squared. So you can't just cancel the 1/2s because they're not in every term. If there was a 1/2 in every term, you could have dropped them off. But there's no 1/2 in front of the GYI, so it doesn't get rid of it. So when you multiply everything by 2, there ends up being an extra 2 here for that reason. The 2 times the 1/2, remember this 2 getting distributed to this 1/2, 2 times 1/2 is a 1, there's a 1 here. 2 times 1/2 is 1, there's a 1 there really. And our goal is to find the velocity of the diver when he hits the water, so just take the square root and you get VF. Okay, the answer for this I'm going to give you for the sake of time. 2 times 9.81 times the initial height of 8 meters plus the initial velocity of 4 squared, all under the square root, gives me 13.15 meters per second. Now remember, this is the speed. This is the speed. This number in magnitude has to be bigger than the velocity he started with. 13.15. Yes. Why? Why does this number have to be bigger than when we started? Remember, what was the initial velocity? What was the initial, what was it? 4. Yeah. If I got an answer that said my final velocity is 2, that means that I would technically have slowed down, fallen, right? But everybody knows conceptually, if you drop an object, what happens to it? It doesn't slow down. It speeds up. So theoretically, this is, yeah, the angle is technically down, so it really could be a negative value. I don't even care about that right now. I'm looking at the speed. The magnitude of this number has to be greater than 4, and it definitely is greater than 4. Okay? It definitely is greater than 4. Speaking of 4, I have about 4 or 5 minutes. Let's go to the next example, number 4. Who would have thought? You're going to watch this example and the next one. If we don't finish this, watch the rest of it. Okay? It's already under Mr. Howell's videos, you'll see there. So you want to shoot a rubber band at Benno. At somebody across the schoolyard from an elevated window. So you're at the window level. Imagine you're like outside the jug yard on the second floor, outside like, when you go down the stairwell, the windows are open, you can see the jug yard. So you've got a rubber band. You're about 7 meters above the ground, so about 2 floors, 21 feet-ish. The rubber band has a mass of 3 grams. You're shooting at its classmate. The classmate is 2 meters tall in height. You know that you can stretch the rubber band a distance of 10 centimeters. If the rubber band, right, 2 centimeters, you can pull back. If the rubber band has a spring constant, a very small spring constant, because the rubber bands are very weak, of 0.2 newtons per meter, with what speed will the rubber band hit your classmate in the back of the head? Okay? I made this one up when I was, I don't know, thinking about all those students that always give me a hard time, I'm kidding, obviously. All right, so in the beginning of the problem, you are at a certain height. Okay, you're at the window up here. Here's your classmate down here. Your classmate is standing here. Your classmate is how tall?
2 meters.
With energy, nice. The height that you're standing at is 7 meters. Okay, so in the beginning of the problem, you could either call the ground level, or because you're going to hit your friend in the head, you can call it where his head is ground level. Doesn't matter. Either way works. You'll still get the same answer. Okay? So again, you can call either of those ground level. Now, in the beginning, you've definitely got potential energy because you've got height. Now, you're not given an initial velocity because you don't have an initial velocity. You have a stretch in the spring. And as soon as you let go, the problem starts. So technically speaking, the initial velocity is 0 at the beginning. Remember, you're holding the rubber band. What's the speed when you're holding the rubber band? 0. But it's got energy in the rubber band, and there's energy due to the height. So in the beginning of this problem, you have PE You also have PES, potential energy in a spring. In the beginning of this problem, you have potential energy due to the height and the spring. There's two types of potential energy to start this problem. Now, if I call your classmate's head ground level, then I don't have potential energy at the end. All I have is kinetic, because the rubber band is moving. But if I call the ground level, then I technically have potential and kinetic energy at the end. It doesn't matter. It really doesn't make a difference. It's easier if you make the person's head ground level. It really doesn't matter though. For the sake of this, I'm going to call this ground level right here. So what's the actual starting height with respect to ground level then? What is it? 5 meters. Yi is 5 meters if I call the person's head ground level. The rubber band has a spring constant of 0.2 newtons per meter. The rubber band can stretch a distance of 10 centimeters. That's your x value in the 1/2 kx squared. Remember, it's how far the spring stretches. 10 centimeters is 0.1 meters. You also know that the mass of the rubber band is 3 grams, which is 0.003 kilograms. So there's the mass is going to come into play now, right? We have to consider the mass of this object. So we've written down every piece of information we know. Let's go ahead and look at our formula. We've got potential energy in the beginning. We've got potential energy in the spring or the rubber band in the beginning. And when it hits the person, it's all kinetic. Why do I know it's all kinetic? Because I'm calling the person's head ground level. If the person's head is ground level, then we know that it must have 0 potential energy at the end of this problem. Potential energy to start with is always mgyi. Energy in a spring is always 1/2 kx squared. Velocity is kinetic energy is always 1/2 mv squared. Now, notice, please, mass does not cancel. Why not? It's not in every single term. It's the spring that's throwing us off. And we are trying to figure out the final velocity. You could plug in if you want. You could plug in all your numbers. You can plug in your mass, gravity. So the mass would be 0.03, a 5 here. God bless you. The spring constant, the amount stretched. Plug in the mass to solve for VF or solve generically. I'm going to solve generically. I always do that if you've picked up on by now. 2mgyi plus kx squared equals mvf squared. Again, what did I do? I multiplied by 2. I distributed the 2 to both of these here. Okay, giving me that next line there. The 2 times the 1/2 cancel each other out. I divide by mass. Gets rid of that mass on the right-hand side. And I want to get VF by itself, so I take the square root of this answer. Okay, I did this in steps, so if you didn't see what I did, I'll point. So I had mass here. I divide both sides by mass. Right, so I divide by mass on this side also. Those cancel out, those masses. Then I'm left with VF squared. So I take the square root of both sides. The square root and the square cancel, so I'm left with just VF, which is what I'm looking for. The velocity that it hits my friend or your friend or whomever it is in the back of the head with. What you're going to recognize is, if you plug in numbers earlier, the spring energy is so little. A rubber band itself has a very small K value. The amount you stretched it is only 0.1 meters. So as a result, what you're going to notice is that the energy from here is very little. The VF really comes from the potential energy of height. That has more of a weight on this problem. Okay, you'll get a number for this when you solve this. So again, finish watching this video and then tonight, and then you're going to finish the 5-3 homework over the weekend.
Since your friend is 2 meters tall.
You obviously kind of wave, but you're still talking, like, and then you do this.
And I paused.
It's really funny.
So an object with a mass of 4 grams is slid across a rough surface with a coefficient of friction of 0.5 of a lab table. If it starts moving due to a spring with a stiffness of 15 newtons per meter, relatively strong spring, compressed 12 centimeters, and then released, how far would have traveled when it is moving with a speed of 4 meters per second? This was elaborate. So the diagram was really important. That's probably why I spent some time, because you have to know what's going on. So it's connected to a wall with a spring. Here's the spring. Here's the object itself. That's how you just draw springs connected to the wall. So the spring has been compressed. It's then released. the object starts to move this way. So at a certain point in time, here's the object. At this point in time, it says how far will it have traveled. So distance from center to center is what we're looking for. When it's moving with a speed of 4 meters per second, so at this instant it's still moving. It has not come to rest. This is different than the Tom Cruise sliding across the floor example with the new socks, right? Well, that example was also
I feel
Tom
like we should have
Cruise.
a Scientology class.
So
To complete everything.
So the velocity here is still some value. It has not stopped moving. We've not lost all the energy due to friction, but we have some friction involved in this problem. So in the beginning, there is potential energy due to the spring. That's all there is. There's no motion in the beginning. And as it moves a certain distance, it loses energy. How does it lose energy? It loses it to friction. So there's some work done by friction from here to here. Okay, some Q loss. Very good. So in this problem, we can start by saying the mechanical energy before equals the mechanical energy after. But we have some loss of energy. Okay? What kind of energy does it have before? It's got spring energy to start. Potential energy in a spring. Once it has moved a certain distance, it's now got kinetic energy because it's still moving. But it has lost some energy due to work. Energy lost to work is FD cosine theta. So remember, Q loss in this problem is work. Work done by friction. So F is really FF, right? Force of friction. By the way, this is kinetic energy final, I should have put here. What's the formula for the potential energy of a spring? In a spring? Very good. 1/2 kx squared. So, potential energy in the spring equals kinetic energy of the object. Why am I saying F even though the object hasn't finished moving?
Because it's your end of your problem.
Exactly, Caroline. At the end of the problem we are considering. Remember, the beginning of the problem, the object is stored against the spring. It is released, it slides, and then we're figuring out the velocity at a certain instant. Now you can continue to watch the video. If you didn't watch these examples, you better get on it. You're going to get lost on the test if you don't do this with springs, I'll tell you right now.